Hey everyone, welcome. Today we're going to pull back the curtain on a key pre-calculus concept that, believe it or not, is secretly running the show in our digital world. We're talking about unit vectors, the secret to digital direction.
So let me ask you something. You're playing a video game, right? Ever noticed how your character moves just as fast when you jam the joystick diagonally as when you push it straight forward? I mean, it seems obvious, but trust me, it's definitely not an accident.
Well, the reason for that super smooth, consistent movement, it all comes down to a really powerful tool for math. It's the secret sauce that keeps game physics feeling fair and, predictable. So yeah, let's dive in and see what's really going on under the hood.
All right, to get the big picture, we've got to start small. I mean, really small. Think of these as the absolute fundamental Lego bricks of the entire 2D vector world. It's time to meet vectors I and j.
So what are these things? Well, it's incredibly simple. The vector I is just one single step to the right. That's it. And vector j, well, that's just one single step straight up. 1 unit horizontal, 1 unit vertical. These are our foundational pieces.
And what's so cool is that with just these two, you can build any 2D vector you can possibly think of. For instance, a vector like 3, 4 is really just saying, take 3 of those I steps to the right and add 4 of those j steps up. So we can write it as 3i plus 4j. It's just a clean, simple recipe for where to go.
Okay, so that's all fine and good, but it brings up a really important question. Every vector has a direction and a length, right? A magnitude. But what if we only care about the direction? What happens when the length just gets in the way? Or what if we need all our vectors to be, the same length?
And that, my friends, is where the hero of our story comes into play. We need a way to create a unit vector. Think of it like a perfectly standardized measuring stick that keeps the direction we want, but locks the length down to exactly 1.
So here it is, a unit vector, and you'll often see it with this little hat symbol on top, is nothing more than a vector whose length is exactly 1. The process is called normalization, and the formula? It's beautifully simple. You just take your original vector and you divide it by its own length. That's it.
Okay, theory's one thing, but let's actually get our hands dirty with an example. We'll grab our vector from before, v equals 3, 4, and we're going to find its unit vector.
All right, let's do this step by step. First up, we need its length, its magnitude. We just used the Pythagorean theorem, the square root of 3 squared plus 4 squared. That gets us the square root of 25, which is just 5. Easy. The length is 5. Now for step 2, we just divide our original vector, 3, 4, by that length of 5. And there you have it. Our unit vector is 3/5, 4/5. Now this new vector points in the exact same direction as 3, 4, but if you were to check its length, you'd find it's now precisely 1. We've standardized it, put it on a level playing field with any other unit vector. Okay, so that's one way to handle direction, but there's another really powerful tool in our toolkit, using angles. This is kind of like giving our vector its own personal compass. So this direction angle, which we call theta, is just the angle the vector makes starting from the positive x-axis and going counterclockwise. The formula is pretty straightforward, inverse tangent of the y part over the x part. But, and this is a huge but, you see that warning on the slide? You have to pay attention to the quadrant. Let me show you why. All right, let's try one out. We need the direction angle for the vector v equals -2i plus 2j. So we're looking at the vector -2, 2. So you go to your calculator, you punch in arctan of 2 divided by -2, and boom, it spits out -45 degrees, which gives you a reference of 45 degrees. Easy, right? We're done?
Whoa, hold on a second. This is the classic trap everyone falls into. Just think about it for a second. The vector is -2, 2. That means we go left 2 and up 2. That lands us squarely in quadrant 2, but an angle of 45 degrees is over in quadrant I. Your calculator, well, it's kind of dumb. It has a limited view of the world and can only give you an answer in a certain range. It doesn't see the whole picture.
So here's the deal. We have to be smarter than the calculator. We know our vector is in quadrant 2, so we have to make an adjustment. We take 180 degrees and subtract that 45-degree reference angle our calculator gave us.
And just like that, we get the real answer. The true direction is 135 degrees. See, you always have to check your quadrant. Don't let your calculator trick you.
Since we just dodged a major bullet there, let's do a quick-fire round of the most common mistakes I see people make with these concepts. Here are 3 quick tips to keep you on track.
First up, simply forgetting to normalize. If the question asks for a unit vector, its length has to be 1. No exceptions. Next, the big one we just covered, getting tricked by your calculator into picking the wrong quadrant. And finally, a simple one, but it happens, mixing up I and j. Remember, I is your horizontal, j is your vertical.
All right, we've been deep in the math, but let's zoom back out. Let's bring this all full circle and go back to that video game question from the beginning. Why does any of this stuff actually matter in the real world?
So check this out. On one hand, you have the naive way. A developer might just add the right and up vectors to get 1, 1 for diagonal movement. But the length of that vector is the square root of 2, about 1.41. That means your character would move 41% faster diagonally. That's a huge difference. But the pros? They normalize it. They use the unit vector, then multiply that by the character's speed. The result? Perfectly consistent speed in every single direction.
And that right there is the whole point. Unit vectors are about pure, unadulterated direction. They are the great equalizers. They remove length from the equation so we can have fairness and consistency in everything from game physics and computer graphics to complex engineering simulations. So now you've seen the secret code that guides movement in all these digital worlds we love to play in. I'll leave you with this. Now that you know what to look for, where else out there in the real world, from the wind pushing on a skyscraper to the path of a satellite in orbit, where else do you think these secret vectors are at work? Something to think about.